by apologizing to everybody whose whose references aren't mentioned in here and so on and so forth. These slides we made on a short notice, and so basically, unfortunately, we did not get enough time to give everybody the credit that they deserve. Okay, I'm simply just advertising these two papers that we have posted. One actually came out in, when was it, November last year, and the other actually just came out literally last night. And so what we are going to do here is basically try to tell you a story about a different way of doing early universe cosmology, which actually addresses the cosmological problems, but while perhaps in some sense a little bit more tuned than inflation, may actually be simultaneously more predictive than inflation, or at least be more testable. So let's start a little bit with some kind of a background about this and so on and so forth. Why do we care about inflation? Basically, inflation was originally invented as, when it was invented, it was accepted very broadly and very quickly with the intent to use it as a dynamical way to essentially outlaw very unfavorable initial conditions for the creation of large, long-lived, smooth universes that essentially plague GR. It's been known well before the advent of inflation, at least in some sort of a organized way, as early as 1973, okay, that in fact our universe is a set of measures, 0 and GR. Essentially, the problem is that if you assume, virialized initial conditions and run them through Einstein's equations, the gravitational instability, even though gravity is weak, the universe is old, gravitational instability is quick enough to mess things up significantly and seriously. And in this, as a sort of side comment, in this paper by Collins and Hawking, there is a rather remarkable paragraph at the very end, essentially invoking anthropic principle as early as 1973 to explain the origin of the universe. So no wonder that 7-8 years later, when inflation finally popped up in a coherent fashion, people jumped on it. Essentially, what inflation does is effectively it takes a log of the cosmological fine-tunings. And while it is somewhat tuned as well, the fine-tuning that you need to do is far less severe than what you would have to do without inflation. And so in this sense, actually, the issue of cosmological naturalness, of initial conditions and the origin of the universe, can be translated into a statement of the naturalness of the dynamical theory, the effective theory that describes the dynamics of inflation. Now, building models of inflation in semi-classical gravity, essentially what I mean by that is take a field theory, do full quantum field theory, etc., couple it minimally to gravity, consider, for example, corrections of the field theory to the stress energy tensor and so on and so forth, but ignore quantum gravity effects. It's very easy to build models of inflation. You just take some inflaton with a flat potential, you make it coupled derivatively to everything else, and you're done. If it's coupled derivatively, if it's initially flat, there is an approximate shift symmetry that is going to protect the potential of the inflaton from getting steep corrections. And also gravitational corrections are also basically very soft because of general covariance, because of the fact that essentially gravity couples kind of derivatively. The troubles arise when we turn on full quantum gravity. In the current law, the statement, this has a long and interesting history, and in fact, actually, dates back to I'm going to say at least as early as early 80s and so on. And it was realized, for example, with the advent of the early wormhole calculus and so on and so forth, that there are problems with essentially preserving global symmetries because there are no long-range heads that protect their charges from simply just popping off into some other universe via wormhole and so on. And such effects, when taken into account and added to an action, can actually lead to significant corrections which are not simply controlled by derivatives. They come from additional considerations and so on, and they can give you large corrections to the potential. Since I just saw John, I will remind everybody of John's early papers from I think 1982 or so on and so forth that actually had a nice way of describing what the issue and the problem was.
I'm not quite that old, Emmanuel. But yeah, it's a bit.
Thank you very much for reminding me of that too. Maybe it was a little bit late 88. I don't remember. Okay?
Yeah, late 80s.
Yeah, there you go. Okay.
Well, incidentally, can I say Zeldovich made these points actually in the 70s, and people claim that Wheeler was also making these comments back in even in the 60s.
Well, yes, right. I was about to mention there is a paper nowadays that gets to, in a way, it's been sort of resurrected. It's Wheeler, Misner, and
yes,
somebody else. I can't remember the third author. I mean, I'm a bit ashamed of that, but that's okay. What they're basically talking about in that paper is essentially, charge without sources, and essentially this whole idea of Wheeler's, the obsession he had about geons and charges without sources and so on and so forth, where he was essentially trying to reformulate not only gravity, but in fact actually all of field theory in purely geometric ways. And maybe a dynamical theory of space-time needs to be reformulated in that way anyway. So I'm not completely sure about this. But basically, essentially what it seems to amount to is the necessity of the inclusion of topological defects in quantum field theory and discovering new regimes of quantum field theory and so on and so forth. And if you go that way, it does appear that it is very difficult to preserve global symmetries from the inclusion of such geometrical contamination, so to speak.
Yeah, I agree completely. But Anthony, can I ask you a physics question on one of the things? I don't know what you want to do on your next slides, but can I ask you about the naturalness issue in inflation?
Yes.
So, I mean, as you know, one of the criticisms is about the initial conditions and just how carefully you have to arrange the initial conditions. And of course, now that we know the Hubble scale of inflation has to be substantially below the Planck scale because of the gravitational wave constraints, certainly people like Penrose and of course Steinhardt and others would say there's an exponentially bad tuning of initial conditions of inflation. Now, maybe not as bad as the gain from the later period of inflation, but still it still looks like a very unusual initial condition. Are you going to address that issue in
No, not really. I will give you a few comments about this, but not much. Actually, I'll just sort of throw in, who's to say what naturalness is when it comes to quantum gravity? Many of these arguments of Steinhardt and so on essentially are based on extrapolating behavior of classical solutions to the regimes where they might not really apply.
Yes, and similarly also Penrose. But Penrose claims, of course, if you're thinking about entropy, why aren't we dominated by a universe full of black holes to start with? Or
yes, perhaps. On the other hand, there are also these recent explorations of the of the efficiency of inhomogeneities and anisotropies in preventing inflation and blocking inflation and so on and so forth. And there are some indications that, if you essentially, I think I've always thought of this as an application of the cosmic no-here theorem. Mm-hmm. If you are in the regime where you have essentially a pretty hard, vacuum energy, cosmological constant or something, okay, it may actually resist the tendency of the inhomogeneities to collapse the universe. So this is certainly true for the anisotropies, and this is a very precise statement. Recently, we have had some more precise statements, in the work of Linden, Senatore, Kleba, and so on and so forth, Flauger, etc., etc. So I think there are some indications that maybe those initial inhomogeneities aren't quite as dreadful as they may be. That doesn't mean the problem is completely solved. Okay.
Fair enough. Thank you.
So I think the fair answer for me is I don't know. One possible way to deal with this is, self-reproduction and these landscape things and so on and so forth. I don't really want to go there yet. Okay, so I'll leave this question as an open question. I will simply assume that, in some region of the universe, we will find sufficiently favorable initial conditions, and as long as we have a natural field theory in the usual, more or less usual sense, then we'll we'll start running away from there. Okay.
Thank you.
Sure. So one of the issues, of course, that I do want to address to some extent is basically, since if it's true that non-global symmetries survive. And I want to actually phrase that a little bit more rigorously further down the road, okay? what are the dynamics that protect put it this way, favorable types of effective theories of inflation that we need in order to be able to have some kind of an attempt at building up a story to start with. So one possible answer that I would like to advertise essentially is monodrome inflation, which is really basically promoting many of these symmetries that we need into gauge symmetries, and then those gauge symmetries presumably survive the adversities of quantum gravity and continue being operational, effectively protecting the low energy theory in a way similar to these global symmetries that you need in the more conventional approaches. And in that sense, perhaps you can view these global symmetries as accidental global symmetries that arise after the gauge symmetries are spontaneously broken. So let me formulate the issue. Let's look at, of course, this is just a quadratic, potential and so on and so forth. This is, in its simple form, not a good theory of explaining the data and so on, but it is sufficiently simple theory to illustrate the issues. So imagine that we start with a quadratic potential, and just to sort of get an idea of, what the questions are, what the challenges are, let's actually consider the phase space dynamics of this quadratic potential and look what it is that needs to happen with the initial conditions for the inflaton for the field phi in order to give it a chance to drive inflation. Okay, so basically this is a well-known thing. In order to have inflation, you need to be in slow roll, even if you actually have a large momentum / velocity of the inflatons dropping down the potential. If you are sufficiently far away and there is enough field range for you to run through, okay, through near exponential expansion, you will be able to bleed enough kinetic energy outside of the initial velocity of the field and end up getting potential dominated. And then while you're potential dominated, your energy density is taking that of the vacuum energy and leading to effective anti-gravity, which we also call exponential expansion, okay? The region of the phase space where this can occur is actually relatively small. It's basically this green wedge, more or less, okay? And it needs to be at distances that are at least Planckian, okay? That are at least order 1 in Planck units. In fact, presumably more. If you play with the potential and take some random polynomial potential, what you will find is that if you wanted to produce at least 60 folds of inflation, depending on the power n of the potential, you need to be initially at where your kinetic energy, where your potential dominated, at least at a distance which is given by a square root of, well, a non-negligible number. Okay, for a quadratic potential, this is roughly, I don't know, number of order 10. So you need to be about 10 units of m Planck away from the origin in the field space for phi to give you a shot at getting 60 folds. If you want more, you got to go out further. And if you have a steeper potential, you got to go out further, and so on and so forth. And so now the question is pretty obvious. Since we're introducing a scale that is above the cutoff for gravity, okay, can we actually trust the theory there? And this is not entirely clear. And we need to have some argument. Oops, something happened here. I'm sorry. We need to have some argument which is going to tell us, why would we have a chance of realizing this at such large field displacements. Enter monodrome inflation. What is monodrome inflation? Monodrome inflation effectively is a setup where you actually utilize gauge symmetries in order to argue that such large field displacements, large field values are not completely out of control, okay? The word, of course, means a single road, effectively. Or if you look at Wikipedia formally, it's translated as running around singly. So instead of, having short paths and so on and so forth, you find a way of how to actually, even though you live in a technically compact space, okay, of small linear extension, you wind around it a lot and therefore realize a very large field displacement simply by just moving around. If we start with a very simple realization of monodromy as an effective theory, something called the flux monodromy and so on, actually there is a very cute way of realizing why this works and how it works. basically by correcting the previous example of a simple quadratic potential, okay? So this flux monodromy effectively is a theory of a massive, okay, a massive 4-form field strength, which can be written in different ways by performing various dualities on the field variables. And one of the ways to write it down is essentially through the introduction of a non-dynamical 4-form kinetic term and a massless Goldstone boson, and then basically introducing a mixing term, whereas the Goldstone mixes with a 4-form field strength, and as a result becomes massive. You can also dualize the electric field strength of the 4 field and replace it with a magnetic field strength Q, okay? And then in those variables, the effective potential turns out, the effective Hamiltonian for the theory turns out to be this. Notice, of course, that this Q is a quantized variable. It's basically given by an integer multiple of some fundamental quantity which has dimensions of mass squared. I'm going to put little capital M as opposed to mu to make a distinction. What this is, this Hamiltonian is actually nothing else but the Hamiltonian describing the motion of a particle in a magnetic field, okay? And the energy levels associated with this, when you quantize it, are nothing else but the Landau levels, okay? So what happens with the orbits, the quantum orbits of this, actually, which also reduce to classical ones when you take large field occupation numbers, okay? Essentially amounts to, on top of your little ellipse in the phase space in the plane phi, p phi, okay, amounts to building a stack of these similar orbits which are offset to a side, where basically as you're increasing Q, you're shifting the center of the ellipse further and further to a distance, okay? This is actually the statement that you're being able to accomplish a larger displacement of the field farther away from the center that is effectively increasing the field displacement from the minimum. Notice that the total field that plays role of the incluton that tells you, that measures the potential energy, is actually the sum of this Q plus mu phi, okay? This is effectively your incluton, phi, that is going to play the role of the field which is slowly relaxing back into the minimum and giving you enough energy. So how is this working out in terms of the energies and orbits and so on? In the case when if we ignore this mixing, if we just stuck to a simple quadratic potential and so on and so forth, we would basically have a theory that has a single branch. Imagine just looking at this green parabola, okay? Now, the usual statement that we have seen previously is that if you want to have any inflation at all from a field which is displaced from the minimum, so here is your minimum, okay? Here is a field on this branch which is displaced from the minimum. If it's displaced by less than a unit of M Planck, you will have no inflation whatsoever. In order to have a chance of getting inflation, you need to displace it much farther. You need to actually go beyond the Planckian scale over to some regime where the field is much larger. And of course, you worry that you have no control in this regime because of the fact that this is at Planckian scales relative to way above the cutoff, and so all kinds of corrections can come in. The statement about monodromy is that it provides you a discrete gauge symmetry, which allows you to fill up this region with additional copies, with additional branches of the branch that you started with. So technically, okay, when you started originally with your field phi, okay, at some value which is sub-Planckian when you were on the original n equal to 0 branch, if you consider that same field value will also be realized on a different branch with a minimum shifted far out, okay? And relative to that branch, the field sitting right here will in fact be at effective super Planckian displacement far from this minimum, allowing you to use its kinetic energy, to actually dampen its kinetic energy by the potential energy and giving you some efforts of inflation. In order to do that, you have to do a little bit of choosing, okay? You have to do a little bit of model building. You have to pick, okay, this mass scale. Let's say it's some relatively high scale, but it is a sub-Planckian scale. You take some number of units of magnetic flux of the 4 form, okay? such that the total energy density in this is still sub-Planckian. But then you realize that the effective field displacement, okay, is in fact given by a seesaw scale between the mass of the field phi, between the effective mass mu, and the mass scale capital M, which controls the magnetic field charge of the four form. Okay, so as long as this is significantly smaller than capital M, you can quite readily get the effective field displacement to be super Planckian without ever truly leaving the sub-Planckian dynamics at all. In a way, you're realizing field displacement in a way that is similar, that is morally similar to building an elephant. Okay, you're giving it a large quote-unquote baryon number. Okay, essentially making it built out of the large units of flux, and retaining the dynamics under control by employing these gauge symmetries, which are unbroken even by quantum gravity. Okay, so that's the general idea here. Now, there are, of course, there are all these kinds of issues that are coming from trying to realize these from first principles, top-down embeddings and constructions and so on, that involve many details, such as getting these scales to come out, getting rid of the additional degrees of freedom, keeping their back reaction under control, and so on and so forth. Okay, there are problems, but there are also opportunities. For example, if you actually take a look low energy theory and start introducing higher order corrections that appear in form of irrelevant operators and so on, renormalizing the theory, okay, oftentimes you actually find that they're not always detrimental, but actually maybe helpful in the sense that they are in fact leading, instead of steepening of the potentials, to their flattening, okay? And this can prolong inflation and help with inflation somewhat, but can also help with the data. Ultimately, our attitude here is that it's really the data that need to be treated as the judge of the theory. You know, we can say data aren't kind, they're neither kind nor cruel for that matter, they're indifferent. We look at them, we take them, and we see how far it goes, and use them as a way of evaluating what's going on. All right. One of the problems clear from this, that should be clear from this, is that in principle, we need to go to these super Planckian distances. Monodromy helps with the argument as to why these super Planckian distances may not be entirely unrealized, okay? We can also argue that as a result of flattening, we are getting potentials which are more supportive of inflation. But it should be quite clear that given some of these concerns about whether you can get any number of units of M Planck, or, you know, the criteria for just what it means to be super Planckian, what's prohibited and so on and so forth appear to be unclear, at least to me at this point. A simple-minded attitude may be try to get help from every corner you can, okay? One of the issues is going to super Planckian distances. It stands to reason, since we don't really have a precise top-down corrections and so on, but also even if we did, it would be difficult to imagine that we can basically say that, okay, anything that is 1.2 units of Planck scale is ruled out. Okay, I don't know what it means that you have a problem with the Planckian displacements. 10 Planckian units is a problem, maybe 3 Planckian units is a problem. Maybe, I don't know exactly, but it does appear that as a general rule, the shorter you move, okay, the better your chances to realize a consistent model. Another issue, of course, is the pressure from the data. And this is where the data simply come in and tell you what you can do and what you cannot do. The trick is that if you go to large field displacements, you're increasing the potential, and as a result, you're increasing the Hubble parameter closer and moving it towards the Planckian scale. And so as a result, you're producing more and more primordial tensor fluctuations. And those are now pretty strongly bounded by the data. They need to be less than, well, okay, 0.06 or so, okay? In order to decrease this, you need to flatten the potential. If you flatten the potential, then a larger field displacement will increase the Hubble parameter less. But then if you flatten the potential too much, okay, your vacuum energy, your effective vacuum energy driving inflation will essentially approximate cosmological constant better, effectively increasing the spectral index towards blue. The bounds on the spectral index are also quite strong. It needs to be roughly at 0.96. So if you flatten the potential too much, you're going to actually come out from this region. So basically what's happening is that the theories tend to produce, well, single field theories tend to produce predictions points which are essentially outside of the allowed regime. So the idea is, okay, let's try to modify this by essentially changing how the dynamics unravels. So this is how we came up with the notion of the roller coaster. We would claim that the roller coaster helps address and relax both the theoretical pressures and the pressures from the data. Essentially, the key observation is we need 60 e-folds to explain homogeneity and flatness at the larger scales, but it doesn't all have to go at once, okay? It is perfectly reasonable to have interruptions to early smooth inflation and do it piece by piece in different stages, where in the regime between the stages of inflation or expansion, you actually have a total disruption and the universe is in fact decelerating for a while. The point is that the data that we currently have only probe the first 10 to 15 e-folds of the last 60 e-folds that are needed to explain the homogeneity and flatness at the larger scales, okay? So as a result, okay, the accelerated expansion may stop and go, and while this looks like fine-tuning, we can realize it by essentially declaring that the inflaton sector is not a single field, but several fields with small hierarchies between their masses, okay? So far, we have probed only the first stage, okay? So because of this, we have to reevaluate the standard Cmb constraints and try to make interesting predictions for short-scale experiments, okay? So we claim that this is actually a good an outcome because we get new predictions to look for. But even if it doesn't work, we actually end up having at least something that can serve as a straw man to test inflation. And if we don't see the additional signatures that you would not see with usual inflation, perhaps you can essentially develop more confidence in the idea that inflation was happening all in one go. All right. The thing is, of course, this still solves the standard. The interruptions do not prevent you from solving the standard cosmological problems. Here is the two examples that I'll just very briefly go over: the horizon problem and the flatness problem. What's the horizon problem? The horizon problem is basically the statement that the homogeneity scale, okay, essentially grows bigger, faster than the horizon scale if you were in a non-accelerating universe. So the way inflation sorts it out is basically by getting this very rapid stage of expansion early on, which is superluminal, and as a result produces a universe before recombination surface, before the end of inflation. Well, recombination surface here, but in fact, well past it in the past, which is sufficiently big so that everything inside it was in causal contact, and all of our universe is merely a fraction of that initial causally connected geometry, which was formed by the early burst of inflation. Okay, so the idea here is an example of the scale factor. The scale factor is simply undergoing early exponential inflation. Then there is an interruption where you basically see that the concave curve turned into a convex one. This is the period of deceleration in between. Then you have another stage of acceleration and so on. It is basically this exponential blow up that is now obtained from several different steps being combined together that still solves the horizon problem. And you can readily check it by comparing the rate of the ratio of the inhomogeneity scale in the horizon, essentially by calculating how the horizon behaves with multiple stages of decelerated expansion interrupting the accelerating stages. And this is just very straightforward mathematics. Essentially, the point is that if you are in the roller coaster evolution, since the scale factor is growing exponentially quickly as time goes on, this integral is going to be dominated by its lower bound, which means it's going to be approximately a constant times the overall exponential factor, and therefore it behaves essentially just like it does in inflation. All right. Let me skip this slide that just tells you the same thing in co-moving coordinates. here is how you also end up solving the curvature, similarly homogeneity and isotropy problems as well. So in inflation, you basically start with some virialized initial conditions in a small universe, have a period of exponential expansion, blow it up really quickly. This is not going to change in a significant way if you interrupt smooth inflation by periods of the accelerated expansion. Basically, all you need to do is still calculate the omega k and how it depends on time. If you have normal matter, you will actually see that it tends to grow for most of the time, eventually wanting to dominate the universe too soon. At inflation, in fact, during inflation, omega k decreases exponentially quickly, okay? Because of the fact that the curvature contribution to effective energy density goes as inverse 2 powers of scale factor, and the cosmological constant, well, the input and potential energy is approximately constant, and so it dominates. And if you actually end up interrupting smooth expansion, exponential expansion by periods of accelerated expansion, you're going to actually lose some of the dilution of the curvature term by inflation, but not by much. Essentially, what you will do is you will get the inflationary answer, which is now getting to be a little bit larger by the ratio of the two Hubble parameters, which does in fact open up possibilities because it decouples the omega k from delta rho over rho, so that in principle, when you look at the larger scales today, you don't need to expect that the omega k will be no larger than about 10 to the minus 4 when you include the cosmic variance.
Nemanja, can I ask you a question?
Yes.
Which is actually probably connected to your curvature issue here. So
yes,
can you have either one or many of these stages of inflation, separate stages of inflation, be open inflation? So something like, for instance, what you might expect from finishing with a common dilution, tunneling event, and then getting open reverse and doing inflation.
Is affirmative. I cannot give you the precise details as to the kinematics of this, but the answer is definitely affirmative. Mm-hmm. Basically, the reason I'm saying this is that, normally if you actually just plot omega k in co-moving coordinates for inflation, what you need to do is basically you imagine that you have started with some virialized omega k, meaning that omega k was originally of order 1, mm-hmm. Okay? And then, of course, as inflation goes on, you're suppressing it, and then inflation ends, and then after that, it just grows uniformly, mm-hmm. Okay, in co-moving coordinates. And the trick, the reason you need 60 folds of inflation is that after inflation ended, and the relative growth of the omega k term started, it cannot get bigger than order 1% now. Mm-hmm. That's the statement that you need to have 60 folds of inflation. Mm-hmm. Okay. If you want to change the dynamics, if you want to play with this and change the dynamics, okay, you certainly can. You can do many, many different things here, as long as you never exceed that 1%, everything goes.
Yeah, understood. Yeah, which is observational constraint.
So
yeah.
I think it's certainly perfectly possible to actually imagine a dynamics where, one of these accelerated stages is driven by something that, will actually end up where the end of that stage can go to something like a first order phase transition, and you will create lots of bubbles and therefore regions with open inflation.
Yeah,
good. With omega, that locally look like open universes.
Yes, yeah, exactly. That's exactly what I'm asking. Okay, great. Okay, yeah.
I think this is certainly true. Mm-hmm. In fact, ideally, the best outcome would be actually to come up in scenarios where that omega curvature actually comes up to around 1%, but from what we have looked so far, that we don't know how to make that a firm prediction. It's certainly a possibility, but not yet a firm prediction. All right, now let's look at perturbations and the origin of as a source of the origin of structure. And only as an introduction, I'm going to end up shortly, and then Guido will take over and give you the details. So with tensors, the story is pretty straightforward, essentially because of the equivalence principle. You have metric, the metric can fluctuate, the theory is covariant, gravity is dynamical, it'll do what it does, okay? And you're going to get delta rho over the tensor in exactly the same way as in common inflation, okay? Of course, there is a question of preserving them. This is why you still need 60 e-folds, even though they can be interrupted, okay? If you had, for example, only 10, 15 e-folds, you had these original fluctuations early on, they get stretched to super horizon distances, they freeze, but if there is not, if they don't stay frozen, until a very late time when they re-enter the horizon, they will not retain their scale invariance. So you still need 60, but if you interrupt these 60, the ones at the largest scales, okay, will nevertheless remain frozen throughout as long as the interruptions are not too long, okay? And this is why in the paper, when we are talking about the details, we're saying we need about 60 folds of inflation. We can interrupt them with, we modeled it with radiation domination, but that is by no means a necessity. You can also, in the second paper that came out, actually, the interruption in between the two stages was effectively like matter domination. The important point is it shouldn't be too long, because if it's too long and the modes that were frozen previously start re-entering during that stage, you're going to start losing scale invariance at those scales, okay? So the scalar perturbations, let me just do something, I'm sorry. Spammers, this is pretty ridiculous, okay? So the scalar perturbations, in fact, are much more model dependent. They're basically a dynamical input that you have to provide to the theory by telling by saying something about effectively the order parameter which controls the approximate vacuum energy driving these stages of acceleration. Okay, it could be your inflaton field, but it could be some composite degree of freedom, some collective degree of freedom. I don't know, it doesn't matter. The important point about it is that it needs to be inserted externally into the theory, because GR by itself doesn't have a scalar propagating scalar mode whose dynamics can do it by itself. Okay, we typically model this as a scalar field to preserve covariance, and we decided not to be too original here. With multiple stages, of course, we need multiple such fields, one for each stage of acceleration. This effectively, in the minimal sense, leads us to multi-field inflation. The fields need to be hierarchical in order to essentially start taking over the control of the evolution of the universe at different times. This is a fine-tuning, but this is not an infinitely precise fine-tuning, okay? As long as we can protect them from the UV contaminations.
But Nemanja, sorry.
Yes.
But isn't a sort of fairly automatic consequence of what you're having a number of shorter periods of inflation, being that the scale invariance is less good of an approximation in each stage of inflation? So wouldn't we expect, I mean, for most of the inflationary stages to be further away from a Harrison-Zeldovich spectrum?
Oh, yes, in principle, absolutely, but I would certainly agree with that. But as long as that is basically happening at E folds 20 and further down the road, I would consider that a virtue, a prediction rather than.
Oh yeah, no, exactly. I mean, we may get interesting things happen, but it seems to be that this is violating scale invariance, making the possibility of having actually overall a much more.
In fact, I have a slide basically trying to come up with a hopefully elegant way of saying precisely the same thing as the points you're making.
Okay, I'll shut up. Thank you.
So, but I certainly agree with that.
I have a question, but for what concerns the first 10 folding of inflation that you measure in the CMB is exactly the same, as long as they don't re-enter the horizon before. No?
Correct.
So I mean, that's the only thing I measure. What happens at shorter scale, God knows.
Correct. That's exactly. Basically, roughly speaking, if you also add in some information from the large scale structure, that extrapolates beyond CMB a little bit. But basically, what we know is 15 E folds.
Okay. So I mean, a short distance.
Then the rest is basically fair game.
Potential for the inflaton, and I would not know. So.
Well, but I'm sorry, I want to push back on that. I mean, it's certainly possible that in future we could measure much smaller scales. For instance, if there was much larger fluctuations on small scales, we could see, compact structures or black holes,
that's possible. That's okay.
So,
most certainly, if we didn't have it, in fact, actually, Guido will tell you precisely how you can use gravity waves for exactly that purpose. Okay, it turns out that if you I don't want to spoil his show, so let me be patient. Okay, he will tell you that.
Anyway, we are running a bit late, so
let me get to the point of connecting this with the scale invariance. So in order to actually understand how the perturbations go, okay, let's go to a prototype, to the original calculation of perturbations in Starobinski inflation, the way it was done by Chibisov and Muhanov back in whenever it was, 1982. They are old enough and they will not be ashamed by declaring them. Okay, So if you look at the old Starobinski inflation, okay, what it was is just the usual, you know, Einstein gravity term plus a quadratic term. If you actually look at which regime inflation occurs in, inflation in the Starobinski model occurs in the regime where the R² term dominates over the linear term, okay? So in fact, you might just as well, okay, focus on the limit where you ignore the linear term in the Starobinski action altogether and just look at the R² term. Now you may say that's kind of crazy because, you know, why? I mean, R² term is obviously not GR, right? Well, actually, that's false. R² term is GR, just not around the Minkowski vacuum. In fact, if you try to take R² as a theory, as a general relativity to the limit of Minkowski vacuum, you find that the gravitational sector becomes infinitely strongly coupled. The idea is the following. You have general covariance in the R² theory, okay? Then by Weinberg-Witten theorem, you have to have a fluctuating spin 2, massless. It's there, okay? However, it's not just GR. To understand what it is, the trick, of course, is to realize that once you write down the actions for the equations of motion for this from this action, you realize that any solution, once you provide it with a scale, breaks conformal symmetry spontaneously. As a result, there is a Goldstone boson, and it's a scalar, okay? For example, one of the ways of breaking the conformal symmetry spontaneously is by a constant term, by an integration constant, which is just the cosmological constant. So the cosmological constant arises as integration constant, or you may say, in fact, that the effective Hubble parameter on the background is the integration constant that the cosmological constant is expressed in terms of. And then you can actually expand the theory around this background and find out that M Planck, okay, is also given in the units of the Hubble parameter that broke the scale symmetry. And the ratio of the two is controlled by the dimensionless parameter which appears in the action. Clearly, this parameter needs to be big. This explains why this parameter in Starobinski theory has to be quite a big number in order to link the inflationary sector to weak gravity around the Minkowskian vacuum, which you flow afterwards, okay? And this number sets the hierarchy between the Hubble scale, which spontaneously breaks scale symmetry, and the Planck scale. The fluctuating term then is precisely this Goldstone boson, this massless field that comes from the spontaneous breaking of the scaling symmetry. Okay, so as a result, this on the other hand is to leading order the effective theory of scalar perturbations in any theory of inflation. So you may actually say that this is like how should I call it? An example, okay, a prototype, a representative example of the universality class of inflations, where the idea is to actually have inflation that produces scalar perturbations. What you need to do is basically develop a theory that in some regime realizes an approximate scaling symmetry, okay? If the theory realizes an approximate scaling symmetry, then on a gravitational background, the scaling symmetry will be spontaneously broken by the selection of a solution. On that solution, you will end up having a field that fluctuates like a Goldstone boson. If there are additional terms, it may not be an exact Goldstone boson, but a pseudo Goldstone and so on and so forth, but de facto it's a sufficiently flat potential. Of course, the challenge is precisely the statement that you need to get. I think this is related to what John was saying. The challenge is to realize a theory that has that stage or approximate scaling symmetry, which is long enough to give you several e-folds and then keep repeating it more and more. Okay, so perhaps this is why we like the roller coaster idea, because in fact it may be easier to realize this effective scaling symmetry in individual pieces and then put them together than try to get effective scaling symmetry from a single theory that gives you a full run of 60 e-folds without much interruption beyond, you know, throughout all of this, okay? The interesting aside, of course, is actually just to sort of notice that indeed this parameter that sets up the hierarchy between the scaling symmetry breaking scale and the Planck scale, of course, is essentially the measure of the tensor perturbations. It is the model independent sector of the predictions, which tells you just how separated, basically, which tells you that the tensors, the tensor amplitude essentially measures how far from the gravitational strong coupling you are. Okay. So let me stop here. Let me actually now, in light of time as well, let Guido continue with the predictions of this dynamics.
Thank you very much.
Thank you.
I think it's better to continue and then a few questions at the end.
Yeah. Okay. Do you see my screen?
Yes.
Okay, good. Okay, thank you. Thank you, Nemanja. So I'll just continue by illustrating how we compute perturbations in the very simplest case, in which you have a periodic or quasi-periodic series of de Sitter interrupted by radiation stages. And then I will talk about the paper of today, which gives you some more interesting scenarios. How we compute perturbation? Well, we want to quantize the curvature perturbation for the scalar perturbation and the spin-2 part of the metric, the spin-2 gauge invariant perturbation for the tensor perturbation. Notice that, as Nemanja was saying, the tensor perturbation are model independent, whereas the scalar perturbation have in this effective action a mass, an effective mass, time-dependent mass, which depends on the actual realization of the symmetry breaking, as evidenced by the parameter phi dot. Then we quantize straightforwardly, and we get an equation for the mode functions. And it turns out, I will do the model independent discussion for tensor. It turns out that the effective mass or effective potential, so you can see this as same as the Schrödinger equation. However, instead of position, now you have the conformal time as variable. So k square is the eigenvalue, and a prime prime over a is the potential, the effective potential, which in normal inflation would be just a single barrier, which is infinite in the future. Here, instead, we have different barriers, and here I took just one example in which you have an inflationary stage, you have a radiation stage, and then an inflationary stage, and final radiation, reheating, and normal universe. So, since the same equations have the same solutions, you use what you already know from elementary quantum mechanics to solve this Schrödinger equation with continuity of the wave function and its first derivatives, since it's only the second derivative that is not continuous. And what happens is that this is exactly the same as the chronic penny problem, the periodic crystal, as the solution of a periodic crystal, except that here you have anti-tunneling. The initial conditions, which are the Bunch-Davis initial condition in the infinite past, give you a single incoming wave instead of a single outgoing wave in usual quantum mechanics when you have the position. But anyway, this we can solve. And I'm going to illustrate the simplest cosmologia con 4 stagioni, which is the first season of inflation that sets up the Bunch-Davis vacuum, for instance, then some period of radiation, and then in big inflationary stage, and finally we go back to radiation domination, then matter, and our own universe. These horizontal lines are referring to different behavior of co-moving length that we see today. And in fact, let me go back to the potential. You see, there are co-moving lines that are co-moving lengths that are always inside the barrier. Okay, and the solution for this kind of co-moving lengths is just that they are frozen all the way. So this is a normalized absolute value of the wave function. It's the red one. Then you have something that, for instance, gets frozen in the first barrier, then it goes out of the horizon, and then it goes back inside the second barrier. And as you see, the behavior is given by this blue line. And another possible behavior is something that is only frozen at the end of the second barrier, and it's, for instance, given by this green line. Okay, so you solve the equation for different modes, for different wavelengths, and you get several mode function behavior. And then the observable, you want to get back into the power spectrum, and the power spectrum for the scalars is related to the wave function by this equation, where h of j is the Hubble constant, and phi is the phi dot value at where this mode is first frozen. And then for the power spectrum of tensors, you just have the Hubble constant. Of course, this is only an approximation, since as you see here, there may be behaviors in which you first froze, then you go back into the horizon, then you froze again, then you freeze again. So this is only an approximation, but it's just to give you the formula that relates at leading order for the modes that freeze only once during Rollercoster, the power spectrum. And what you get in this simple cosmology is simply that the power spectrum just is constant with respect to the standard inflationary one. Here it's normalized to the Hubble in this stage. And then it goes, but with oscillations, and these oscillations are due to the modes that are not completely frozen right away. And this is the power spectrum in a more realistic case, in which we have several stages. You see, you have oscillations, and then you have a second step, and then you have another step that gives you, of course, other oscillations. So this is what you would expect naively from a multi-barrier potential. And so far, you may say, oh, okay, there is nothing really deep in the prediction. Well, I would say that this is already a non-trivial prediction, since, for instance, if you were able to measure very short scales, you would be able to see that the spectrum is not just a constant, but it goes down. However, probably the more important thing at this stage is that models like power law inflation are now viable again, because for instance, when people usually draw the contours of predictions for an inflationary potential, they go from a number of e-fold 50 or more, because they implicitly always assume that everything goes in one stage. However, here, since we have just a few e-folds where the CMB is produced, and then we go to another stage, effectively the modes, effectively the Scalar parameters that determine the inflationary prediction, and S and R, scalar spectral index and tensor amplitude, are calculated at an effective number of e-folds before the end of inflation, which is much smaller than 50. And for instance, you can have a power law, which is, of course, this is still a concave, this is already a concave potential, because the tensors are very low. But for instance, if you take 40 e-folds of a square root power law, then this is perfectly fine with the data. Instead, it would not if you consider inflation to only be a single stage. You see that the power spectrum is effectively getting redder. You have more curvature. In principle, this may mean that the running of the spectral index can also be observable if inflation is short. So the model building is open again, and still it is a non-trivial job. Not everything goes. For example, if you have exponential potentials, the predictions do not depend on the number of e-folds, and so exponential potentials are already on the verge of being ruled out, even if you assume the roller coaster dynamics. But now let me tell you about more interesting things that you can do rather than just suppressing the power spectrum. For instance, take the monodromy inflation, which is naturally given by motivations, theoretical motivations of being quantum gravity safe, and make it double. This is something that that you expect in string theory construction. If in this kind of two-field model there is a small hierarchy between the two scales, effectively you are decoupling the two stages of inflation. So you first inflate along the phi1 trajectory, then you have these oscillations, which effectively are a stage like one something e-fold long of matter domination, and finally you inflate along the phi2 direction. And what are the CMB predictions of this? This is very, very interesting now, because the solution is easy for this potential, and you see that monodromy inflation is now viable again. If I take the full phase space of this model, the full parameter space of this model, and I fix the number of e-fold to be 55, everything is basically out because the spectrum is too blue. However, if I go to a 40 e-fold stage or just 35 e-fold stage, then I have a big part of the parameter space that's still viable again. And so this is the first interesting consequence of thinking about these multiple different stages. However, now the bump that we have, the matter domination, can be made more interesting. So first of all, we are compatible with SCMB. And not only that, in this particular model, in the monodromy inflation, we are very predictive since there is a lower bound on R. See, you cannot go at very, very small R, because if you push mu down, you will never go to R equals 0. There is a bound which is about 0.02. So we may be already detected or ruled out in the next decade with the CMB stage 4 experiments. But more surprises there are, since in string theory, it is natural to expect couplings to gauge fields. So what is our action? Basically, it comes from compactification of a form in a higher dimension, which also has a Chern-Simons coupling. Now, this Chern-Simons coupling will give you an effective coupling to a dark U1. In 4 dimension, this is the usual coupling of phi to the F tilde operator. It is a dimension 5 coupling. And if you write down the equation of motion for this, you realize that there is a tachyonic dependence of one helicity of the gauge field for fast rolling field. So look at the oscillator equation for the gauge field. So as you see, this sign tells you that for a low K, the helicity with like lambda is the sign of the velocity. So whatever here gets the minus sign gets a tachyonic dependence. So it's exponentially produced with a parameter that is phi dot over F over H. And so basically what happens is that the full solution of the system is very complicated. We know that we have the exponential production for constant phi dot over H. And this is a sketch of how for different couplings and number of E-fold from the end of the first stage, the energy density in gauge field grows. As you see, it can grow by up to 8 orders of magnitude. And here, before this vertical line, we do trust this solution. After the vertical line, you do expect that there is a saturation due to energy conservation, since exponentials are never physical all the way down. So we will trust the solution up to end of inflation, where we switch regimes, and then we should match to a numerical solution. So here, we do expect this to plateau and then go down. There are some numerical studies of what happens, and we have references in our paper. But let me just stress that the prediction up to this line, where the first inflation ended, the first field starts to oscillate, we can trust, and then we know from physical consideration, just energy conservation, that this has to go down. So what are the observables? Well, at small scales, we have both non-Gaussian scalar perturbations and gravitational waves sourced by these vector perturbations. Gravitational waves are chiral, and they are given by this formula. So this formula, which is normalized to the energy density today, has this one. So what is this one? Well, this one is just h over m Planck square, which is the usual tensor perturbation in the sitter, plus the exponential production. And since to make contact with the experiment, I will change variable from the number of e-folds where the wave vector throws to the frequency. And this is the prediction. So the prediction is that if I take NCMB equal 35, which is if I take parameters such that I am in this region of parameter spaces, the blue one, I have a observable R, I have an S which is within CMB, which is within the current CMB bounds, and I am predicting a loud signal for small scale gravitational experiments. Here in particular, I've shown the sensitivity of LISA. If I change the number of e-folds, this plot will effectively shift right or left. If it's like 40 e-folds, for instance, I go right, and then I would fall, for instance, into the sensitivity region of Einstein telescope or the SIGO or other gravitational wave experiments for the future. So let me conclude. We showed you that, hopefully we convinced you that inflation does not have to happen all in one go. Interrupting it, in fact, will help both with naturalness, relieving the pressure from the UV completion, from the usual complaints about what does this do in quantum gravity. Moreover, it definitely helps with the fitting data for the large field models that large field models, let me remind you, are very, very predictive. I mean, if in a few years we see a tensor modes, then these models are probably the most theoretically motivated ones. And the tuning to accomplish this is minimal. I mean, it's basically not much more than having to tune a lot the parameters of a very long stage of inflation. Nemanja told you that the horizon and curvature problems are easily solved. It just amounts to have enough e-folds of the sitter expansion. So in general, the model building reopens. In particular, there's the very exciting possibility of having correlated signals at large and small scales. And it's interesting to ask now, what are the other interesting observables? Let me mention, I don't know, like primordial black holes, for instance, or if we have non-Gaussian scalar perturbations, which we will have in, for instance, the double coaster, this may be seen in future CMB spectroscopy experiments. And an interesting realistic example is the double monodromy, which is a gravity wave factory for CMB and LISA, or generically small scale gravitational wave experiment. And well, let's find more examples. I hope that we inspired you. Thank you.
Thank you very much, Guido. So there is time for extra questions, both to Guido and to Nemanja.
Yes.
So. So any question?
There was one in the chat.
Yeah, there was a question in the chat indeed, but I think it was was old.
Yeah, I noticed the question. Yes, no. The answer is no. It doesn't have to be. The only reason I mentioned the first order phase transition was if you wanted to get the sections of the universe in a late universe that look like an open universe with negative curvature, then something like a first order phase transition would do it, but because you need to make bubbles, and then use the bubble interior homogeneous surfaces that are naturally that naturally have negative curvature. But whether you are going to be able to see it or not, of course, then obviously depends on how many E-folds after the bubble nucleation you have. So I think the full answer to your question, it's an interesting question. I mean, the full answer is we really don't know because we haven't tried yet. And it's actually really an interesting question to try to figure out just what the allowed regions in the phase space are where you can get additional predictions yet without spoiling the stuff that you know, which is namely just the CMB.
Thank you.
Mm-hmm.
So there's a question from Alessandro, so in the chat. Can this
Very good question. I see it in the chat. The answer is unfortunately no. We tried. This is what we call, what did we call it, Guido? This is the, we have written that example explicitly as one of the special limits of the solution in the long paper. Essentially, the reason it doesn't work, the question is, let me repeat the question for everybody, whether you can actually accomplish this with 60 stages of a single E-fold separated by non-accelerating geometries, okay? It's a great question. Unfortunately, the answer is no. The reason is the following. If you have very short stages of accelerated expansion, the 15 modes, okay? Sorry, the 15 E-fold, the CMB modes will in fact start coming in and out of the horizon. Think about the process of it's like you're having I'm gonna call it cosmic permafrost. Cosmic permafrost are these very large scale fluctuations which are expelled out to super horizon scales where they simply sit and wait until they re-enter the horizon. And the reason you want to have it is in order to maintain the scale invariance because of the fact that the amplitude of these perturbations is set by the value of the Hubble parameter at horizon crossing, okay? If you have many stages of a single E-fold, okay, essentially what's happening is you're disrupting this permafrost. The modes are coming in and out of the horizon and getting processed in the way. So in fact, actually, you're going to lose scale invariance pretty efficiently, pretty rapidly. However, one thing that we think you may be able to get away, imagine that you have, let's say, minimum 15 E-folds, 20 E-folds, something like that early on to fix the CMB. And then after that, okay, maybe the remaining 40 E-folds can actually be one E-fold at a time.
Yeah, well, yeah, although the total non-accelerating should be a bit shorter because
correct.
Horizon and
kinematics need to be controlled. One thing that you can also in principle have is, let's say you have 20 E-folds of accelerated expansion early on to fit the CMB. And then let's say you have some very slow acceleration, like, some power law, T cube, I don't know. I'm just throwing a number, okay? As long as you have 60 up to additional 40 E-folds out of there to maintain the scale invariance, the longevity of the scale invariance of the modes expelled during the first 20 E-folds, so as to fit the CMB, it looks to us you should be okay.
Yes. Yeah.
All right, thanks. So there are other questions? So I think there's none. We had a lot of discussions, so I think we can close the session here. Thank you everybody for attending and for giving these two nice talks. Okay, see you.
Thank you, the organizers.
Bye-bye.
Thank you, everybody.
Bye-bye.
Bye.
Hey.
Hey.
Bye.
By the way, Guido and Nemanja, so I recorded the talk. Is it okay?